longer see it.
Good. I'm admiring your scarf because I've become a knitter.
Oh, I think my aunt knitted this.
Welcome back in person, everybody. It's great to see your faces or your masks, as the case may be. So I'm very pleased that our first in-person colloquium, at least our first in-person colloquium here, is Alex Gittens. So Alex is technically, I think, my academic nephew or something like that. So he's a student of Joel Trump, who was a student of Inderjit Dillon, who was a student of Jim, who was my advisor. After his PhD work at Caltech, he went and spent some time at Berkeley in the RISE lab, and has now been at RPI for since 2017, so 5 years. Does really interesting work on randomized computations, randomized numerical linear algebra, all sorts of things that I know a number of you like. I certainly like too, and I'm looking forward to hearing more about them today.
Thank you, David. All right, so the talk today is going to be on some work that I did with my student Kareem Agur, who was co-advised with my colleague Blendenpik and LSRN from the CS department at RPI. So the basic task that we're looking at, I'm sure many of you are familiar with this, is we have a huge tensor, and what we would like to do is find a low-rank approximation to that tensor. So there are all sorts of classical algorithms for finding these low-rank approximations, and we would like to do it quickly and accurately. So ideally, we would be able to trade off accuracy for speed in some principled manner. So this problem is useful for, it's just a building block for a lot of computations. So it's used for data compression, for instance. So if you ran some sort of physical simulation, naturally you might end up with a tensor that you might expect to have some structure that you can exploit to compress it. So you could compress using, or compression using tensors to compression using a SVD, where you could just unfold your data into a matrix and then take a low-rank approximation of that matrix. So tensor low-rank approximation uses exponentially less space than that sort of naive approach. Another application is video background removal. So I was just talking to Philip about this. So the idea is if you take a low-rank tensor approximation of a video, the background stays still throughout the video. So that becomes a low-rank portion, and you can pull that out. So you can subtract the low-rank portion from your video, and you'll be left with the foreground. Okay, another classical example is chemometrics. I think a lot of the algorithms for tensor decomposition came out of chemometrics. Another modern classical example is hyperspectral imaging, where you want to separate a hyperspectral image into different sort of components. The spectral methods in machine learning are used for basically finding moments of graphical models. Okay, so those are some motivations for caring about tensor decomposition. So, some caveats. This is a non-convex problem. It's very different than low-rank decomposition of matrices because we don't have, say, like the Eckert-Young theorem. And even determining the rank, well, what do you mean by rank? There's multiple definitions of rank for tensors, but fix one, and determining it is going to be NP hard. Well, CP rank is NP hard. And sort of the hopeful point that we have is that this is a non-convex problem, but it's multilinear. So hopefully we can use some ideas that we have for how to trade off accuracy and speed in numerical linear algebra and bring it over to the domain of these multilinear problems. Okay, so just to set up what I mean by a low-rank approximation of a tensor, we're going to review low-rank approximation of matrices. So if I give you a matrix X that's I by J, and I ask you to find a rank R approximation, what I'm asking for is for factor matrices A and B, and they both have R columns. A is going to explain what's going on in the column space of the matrix, so it's a basis for the column space of the matrix, and B is a basis for the row space of the matrix. And of course, X in general is not low rank, so I can't hope to get a zero error approximation. So what I try to do is find A and B to minimize the sum of squared errors. Okay? And then I can write my approximation, AB transpose, as the sum of R ranked 1 outer products of two tensors. Oh, by the way, if you have questions that are going on, feel free to ask. Okay, so we're generalizing this to tensor low rank approximation, of a particular form that we call the canonical polyatomic decomposition, CPD. And to do that, what we're going to say is we can generalize the outer product from 2 vectors to 3 vectors, or 4 vectors, or 5 vectors. Throughout the talk, we're just going to use order 3 tensors. So hypermatrix with 3 indices, but you can generalize this to higher order tensors. Okay? So our goal now is, given this order 3 tensor, we want to learn 3 factor matrices. One that explains what's going on in the rows, one that explains what's going on, the columns, one that explains what's going on in the rows, and one that explains what's going on in the depth direction. Okay? And all of these are going to be rank R bases for these spaces. And again, we can't hope to get an exact basis. So what we're going to do is find bases A, B, and C that minimize this sum of squared errors. So that's our Frobenius norm again. And we're going to write this sum of rank 1 outer products using this notation. Okay? So this is our rank R CPD approximation to X. That's not unique. Okay? So what we have, our results that I'm going to talk about in this talk, are we give a sublinearly convergent sort of outline of an algorithm for sketch CPD. So we're going to look at a particular template for getting CPD. Right? This is alternating least squares, and we're going to show how you can sort of trade off accuracy for speed in this template by using different types of sketching. Okay? And that's a template. It's not really achievable because some of the parameters we need in order to instantiate this, we don't know. So these are going to be like angles between the residual of some linear system and the system matrix. We can't get at those. Okay? So what we need is some heuristic for sort of working in the setting where we don't have that information. So we're going to provide a heuristic for adaptively selecting the sketching rate when we don't know these angles. And we're going to show that that outperforms prior attempts to do sketch CPD. Okay? So another way to think of that is there's some hyperparameter selection problem involved in this meta algorithm, and we have a heuristic for that. Okay, so back to caveats. So CPDs, as I mentioned, are different than low-rank factorizations because we don't have the SVD, which tells us everything we want to know about low-rank approximations of matrices. Okay, so in particular, even if I give you a tensor, it's NPR to compute its rank. The CPD of a given rank may not exist. Okay, that can happen. And multiple CPDs can exist. Okay? This is a non-convex objective. It can have multiple local minima. And also, CPDs of rank R aren't in any way related to CPDs of rank R plus or minus. So that sort of sets our expectations. What can we hope to get? So numerically, what we want is algorithms that converge to critical points of our objective. So we're satisfied if we're able to find factor matrices A, B, and C star, so that this is a local optimum. Okay. Minimum, maximum, hopefully minimum. Okay. So the classic algorithm for finding CPD is alternating least squares, and this is a very natural algorithm. So it's a Gauss-Seidel type algorithm. So what we do is, let's say at time t, we have approximations a, t, b, t, and c, t for these bases. Well, we fix b, t, and we fix c, t, and then we minimize the error with respect to a to choose a better basis for my column space. And then I fix at plus 1, I fix ct, minimize my objective with respect to b to update my basis for my row space. Similarly, I fix the previous a, b, and update to get a better c. So the nice thing about this scheme is that it gives us a sequence of low rank approximations where the approximation error has to be non-increasing. Okay, and then under reasonable conditions, you can show that these approximations converge to a critical point. All right, so I said that this is an alternating least squares algorithm, and that is because I can cast each of these as solving a linear system. So I'm going to show that right now. So the nice thing about the Frobenius one is that it doesn't care how I arrange the elements that I'm getting my sum of squared errors over. So in particular, if you give me a tensor, I can flatten it out into a matrix. And I can do that in several different ways. The ways we're going to do is we're going to flatten it out in the first mode, meaning that we stack all of the columns in the matrix together. So this is an example, sorry, the tensor. If this is our tensor, so it's a 4 by 3 by 2 tensor, I can flatten it in the first mode by stacking all of the columns together. And if this was I by j by k, then I see that when I flatten it, I get I by j by k. Okay? And then A is going to be a basis for this thing. And similar, I can flatten to mode 2, so I'll stack the rows together, and I'll get a j by I by k matrix, and B is going to be a basis for the column span of this. And then similarly, I can flatten the third mode fibers in this way, and I'll get a k by I by j matrix, and C will be a basis for that. So when I matricize, let's look back here. Okay, so I can reshape this into a matrix. Then I need to reshape this low rank tensor approximation into a matrix as well. So let's look at how we do that. Okay, so the way that I do that uses what's called the columnwise Katsuri-Rao product, which we're going to write as x circle dot y. And all that is we're doing a column-wise Kronecker product of x and y. Okay? So in particular, if x has I rows and y has j rows, and they both have R columns, because remember, we're doing column-wise Kronecker products, they have to have the same number of columns. What's going to happen, because we're taking column-wise Kronecker products, we're going to have R columns, and we're going to have I times j rows. Okay, so it becomes a tall, skinny matrix. Okay, so in this case, I guess I said x has L rows, y has P rows, they both have R columns, so you get this. All right? So this is a subset of the full Kronecker product. All right, so then some useful algebra facts. You can go through the algebra if you want. If you matricize this, then you get matricize it in the first mode. Then you get A, which makes sense because A is a basis for the column span. Okay. A times B, Katsuri-Rao C, transpose. So this is A is our basis, and then BC transpose is going to be a short, fat matrix. We'll see on the next couple slides. Similarly, if I matricize in the second mode, I get a basis for that mode times the Catch-Arel product of C and A transpose. Matricized in the third mode, I got a basis for that mode times B Catch-Arel A transpose. Okay, so this is all just setting up the problem. Is there any questions on that so far? Nope. All right, so we reshape these problems above and use those identities, and then we get the standard CPE ALS algorithm. It involves updating my basis for the column span by solving this matrix least squares problem. Okay. So this is my right-hand side, and this is my system matrix, and this is the matrix I'm solving for, the basis I'm solving for. Similarly, my right-hand side, my system matrix, to solve for a basis for the row space. Similarly for the, third mode. Okay, so the nice thing about this is if we assume that the rank of our tensor, or the approximation we're looking for anyhow, is much smaller than the size of these three system matrices. Okay, because remember the three system matrices are, this one here is like B Catch-Arel C transpose. It has this many columns. This is A Catch-Arel C, and this is A Catch-Arel B. Those are the number of columns in each of my system matrix. Okay. So if R is much smaller than those, this is what the systems look like. So consider the subproblem to update my factor A. A, remember, is a basis for my column space. So it has I rows, and it's rank R, so it has R columns. So each row of A has R degrees of freedom. But if you look at how many constraints I have, well, these R values have to satisfy JK equalities. So this column, interproducted with this row, gives me this entry. This column, interproducted with this row, gives me this entry. So this row satisfies JK equalities. Similarly, all of these things satisfy JK equalities. But JK is much greater than R, so these are over-constrained linear systems. Okay, that's the key point that we're going to take advantage of to solve this fast. Okay, the same is true for the systems that update my basis for the row space and the mode 3. Okay, so the idea is straightforward. So if we imagined that all of these constraints are equally important, then I could just randomly sample about as many constraints as I have unknowns, and I'd expect that linear system to be invertible. Okay? So then I could solve for A without any loss by solving a much smaller linear system. Okay, so I model this process of sampling constraints by multiplying from the right by a sampling matrix S. And the idea is I can sample S in some ways. I could uniformly sample S if I have more information, like for instance, maybe X is sparse, so a lot of these columns are zeros, so I would not want to sample those. Those don't give me meaningful constraints, right? So in that case, I would choose S to avoid these unimportant columns and focus on the important columns. So there's a lot of different ways to sample S. We're going to be kind of agnostic to that. Okay? But this is the basic idea. We want to sample enough constraints to get an accurate update for A, so we're making progress at every solve, while sampling few enough constraints that it's faster than solving the full system. Okay? So prior work has considered this idea. It's pretty straight. Yep.
So just for setting up what's to come, are you thinking of maintaining the same sample across iterations, or it's going to be different samples?
It's going to be different samples. Yeah, because we want to have everything in expectation, be unbiased, all that nice stuff. So that what we could ask is, do we select the same number of constraints? And the answer is no. As we go along, we're going to typically increase. Yeah.
So since David asked the question,
Yeah.
let me ask another one. I think I understand the global picture here, even more globally. Is it obvious that you should always be going through A, B, C in that order?
No.
Suppose sometimes you already have a good approximation for depth space.
Mhm.
Can you detect it and somehow concentrate on going through A, B, A, B, A, B, A, B?
That is a great question. I have not thought about it, but I think that's a great idea. The question would be, how would you detect it? I mean, you could randomly choose, but that's not any better than doing a cyclic thing, I think. So that's a good question. I don't know. And we'll see. I mean, actually, so one of the things that matters is the conditioning of this system. And you could imagine, like, when you're solving for A, B, or C, you have different condition numbers, and you want to focus on the ones that are ill-conditioned. So maybe that's one sort of way to naturally say I should focus on the updates for this mode versus the other modes. But that's a great question.
Thanks.
Yeah. So this is a pretty straightforward idea. You know, sketching has been around for a long time, and everybody likes to use sketching for problems where it makes sense. So it has been considered before from the, and I'm focusing in particular on ALS algorithms. So second order algorithms. There's first order algorithms that like sketch the gradient descent, right? So we're focusing on ALS. So from the scientific computing community, so Gray Ballard and canonical have a nice approach to this problem, where what they focus on in this is this issue of potentially the constraints are not equally important. So what they kind of do is do some sort of randomized mixing of this linear system before they sample, and that helps deal with that issue. And if I just uniformly sample, I could choose uninformative constraints. So that's their contribution there. But we'll see an issue with this. And then this is a nice piece of work from the theoretical computer science / machine learning community. So Richard Peng and his collaborators have this work on spalls, which takes an opposite view. So here, they mix and then sample. And what they do here is there's a nice way to quickly get importance scores for these constraints. And then you sample according to those importance scores. Okay, so leverage samples, leverage scores if you've seen these before. All right, so yeah, so let's look at those two algorithms as sort of proxies for all the other algorithms. So what they do is they use previous results on sketching for solving linear systems. And all of those results in sketching for solving linear systems, what they say is the way that I trade off between accuracy and speed when I sketch my over-constrained system, the type of guarantee I get is that if I compute my solution to my linear system by using sketching, the error of that solution is only slightly greater than, so it's only a small factor greater than the error of if I had computed my solution using the full linear system. And that makes sense, right? That totally makes sense. So the problem with that is that potentially this means in our application, the error could increase at every iteration. Okay, if we just go ahead and use this theory. Okay, and that would just break the whole idea of ALS. Remember, the idea is that because we're solving sequentially to get better A, B, and C, our approximation error is going down sequentially. Okay, so we try to avoid using this. That's one of our contributions. And then from the practical side, right? Because you want to use these algorithms in practice. All of these algorithms, prior algorithms, used a fixed sketching rate. So before they started the problem, they somehow assumed we chose a sketching rate, saying we're going to choose 70% of the constraints at every iteration. So this goes to David's question, right? So there's that hyperparameter selection problem, because in practice, if you just give me a tensor, do I know that 70% of the constraints is going to work over the entire optimization map? I don't, right? So we have a heuristic for dealing with this. We show it works well. And then I mentioned this before. Because we're solving these linear systems, they can be ill-conditioned. If, say, our A matrix has, all the columns are close to collinear, then when we try to solve the update for B or C, those linear systems will be ill-conditioned, and it's going to slow down the convergence. Okay, so we theoretically deal with this, and then empirically deal with the hyperparameter selection. Okay, so here's an example of what I meant by swamping. Okay, so here we generated a tensor synthetically where we know the factor matrices, and we chose them so that they're collinear, the columns are collinear. So they're going to give us ill-conditioned linear systems in principle. And then we used ALS to recover, or try to recover, these tensors. And then we also used regularized CPD ALS. So by I'll tell you what I mean by regularized. And here we show the results where we're plotting the relative approximation error at iteration t. Okay? So the iteration is where we do a solve for A, B, and C. Okay? So this is just standard CPD ALS. And we see this is what we call swamping. So the rate of convergence slows down due to the ill conditioning. Okay. And this is where we use proximal regularization, which makes your solves strongly convex, so you make more progress. You can see on the next slide, I think. So we added proximal regularization, and we're also using sketching. Okay? So we see that together they work well, and we converge to a much lower relative error in fewer iterations. Yes?
Is there an easy way to check if a tensor is ill-conditioned? Or is that something you know a priori if you want to? Or
not that I know of, no. I mean, ill conditioning is really defined for the factor matrix. Like you have to have factor matrices, I think, to talk about, because again, the decomposition is not unique for a tensor, so I'm not sure. I mean, it can be, right? If some conditions are satisfied, then you know that a tensor has a unique factorization, and then you can talk about ill conditioning. But in general, I don't think it would be well.
I see.
Yeah. Okay, so takeaway from this is regularization is useful in practice because it avoids this swamping issue. Okay, so this is a well-known fact. Okay, and the solution, or one proposed solution, is proximal regularization. So all that does is it constrains your solve, or your updated factor, to remain close to your previous factor. Okay, and again, this makes this objective strongly convex, which helps solve it faster. Okay. Yeah, so this is called the regularized ALS algorithm. There are other alternatives. I could make this strongly convex by just adding a Tikhonov regularization here, and that does help the convergence as well. But the issue is, the nice thing about regularized ALS is that adding proximal regularization doesn't change the critical points. So when you solve this, you converge faster to the same critical points if you have ill-conditioned subproblems. Okay, and again, we found that proximal regularization in practice works well with sketching. So this is from the paper before the one that I'm talking about now. So here, what we're looking at is the ratio of the error that you get when you do sketching plus regularization divided by the ratio of that to the error of just standard ALS. Yeah?
If you could go back one slide. If the lambda parameter is pretty high here,
Yes.
does that mean you're going to be doing more steps?
Yeah, there's some trade-off, right? It's not clear how to choose that lambda. That's another question that, is still open. Yeah, so in my theory, it's not very satisfying because I find you need lambda to be sort of on the same size as the bottom singular value of your system matrix. So it doesn't really help that much, but in principle, it can help. Okay. That's a great question. I don't know the answer to that. In our experiments, we just fixed lambda as like 0.001, and that seemed to work for everything. Okay. Yeah, so what we're looking at here is we're looking at various combinations of sketching and regularization. And on the x-axis, we're plotting the relative error of sketching to just solving CPD ALS and the runtime. Okay? So ideally, we want to be in this green region where our error is better than or equal to using CPD ALS, but our runtime is faster. Okay? And this is what we found. Proximal regularization plus sketching of various kinds helps. Okay? It gives you a nice accuracy versus runtime trade-off. So we want to have some theory for that. Okay, so this is our meta-algorithm. Okay. So remember, we're going to sample constraints, and we're going to use proximal regularization. That's the meta-algorithm. It's meta because there's many different ways of sampling. I could mix and then sample fewer constraints, or I could use importance scores to choose my constraints and then sample, or I could just uniformly sample constraints. And in fact, in our experiments, we just uniformly sample constraints. Okay. All right. So we can ask, what are the related works? Forget about ALS for a second and just consider the structure of these problems. And so I would say the most related works, you can think of this as being, you're taking like a Newton step, second order, but quasi-Newton because we're sketching the hashing. Okay? So there's first, inexact quasi-Newton methods for convex problems. And then there's deterministic block proximal algorithms for non-convex optimization. Then I would say these are a nice class of algorithms if you want deterministic tensor factorization. So it's a natural thing to compare to. Okay, so the first class of problems, you're looking at just solving this convex optimization problem. And we're going to use quasi-Newton method. So we're going to approximate the Hessian and or the gradient of f using sampling. Okay? So the same idea as sketching, and we're going to do that independently. And if enough samples are used, then we'll either see linear or superlinear convergence. That's sort of the class of results. And then these deterministic block proximal algorithms for non-convex optimization consider problems that look like this. Okay? So they assume that you have some regularizers on your variables here. So your variables are divided into groups. In this case, we have a variable for the row space, column space, row space, and the order or mode 3 space. And we have a joint objective that couples them together, but then you have separate regularizers on each block of coordinates. Okay, so then there's a class of algorithms that say if we do this sort of Gauss-Seidel updates, we can do various things for minimizing these. Maybe we linearize this and minimize it instead. Okay, we can say something about the convergence of these. So there's no randomness in these algorithms, as far as I know. And then they assume some knowledge of the global structure of the problem in choosing these regularization constants. And then they guarantee convergence to critical point. And they're nice and easy algorithms to use, so I think it's great. All right, but neither set of these previous works applies to our case because our problem is non-convex. Okay? And then also, the factor matrices that we obtain are going to be biased estimates of the ones that we would obtain from solving the full linear system. So any questions so far? No? Okay, so here's sort of the outline of the whole, I guess, the steps to reaching some sort of guarantee. Okay, so the first thing that we observe is that each sketch least squares solved actually does decrease the objective almost as much as a full least squares solve. Okay? And that's under the assumption that the sketching rates are high enough. So we have to know a certain parameter in order to choose the sketching rate to guarantee that we get a decrease, right? So obviously, if we always choose like 5 columns, that's not going to be a high enough sketching rate. So there's a parameter we need to track in order to know what the sketching rate is. And then we can relate this decrease to the size of the gradient of the objective. Okay? And then once we've done that, we use some standard results because proximal regularization in particular ensures that the size of the gradient is bounded by the difference in the functional values at each step. Okay, and we know that it decreased. So that tells us how much progress we made at each step. And then we can just turn that into a sublinear rate of convergence. So it looks kind of like the convergence rate of subgradient descent. Okay? And we get to an approximate critical point. So after t steps of this algorithm, we get to, or we have seen a point where the size of the gradient looks like 1 over square root of t. That's what I mean by sublinear rate convergence. Okay, and just to point out, this is not like the best possible result because we are doing least squares solves, right? So we would expect that we can get maybe a linear rate if we do a good job of sketching. Okay, so we show we get a sublinear rate, but I feel like you can do better than that potentially. At least locally. Locally, you should be able to say something stronger. Okay, so the first step of this process is showing that the error decreases by some large fraction of the maximum possible decrease. Okay, so let's just introduce some notation to simplify things. This is our update. Okay, this was we sample some constraints. So M here is my system matrix, is going to be B, capturing around C, transpose. I'm just calling it M, so it fits on the slide. Okay? And then I use some regularization. Here, in principle, I allow the regularization to change between steps. Okay? So the important thing is I consider the residual from the previous estimate of my basis. Okay? And the best that I can do is to update A so that this residual, as much of that residual as possible, is captured in the span of the system matrix. Does that make sense? I can't update A to capture more of the residual than is in the span of M. Okay? So that's the best possible thing that can happen, is that when I update A, the objective goes down from the previous A by exactly this much. This projects R onto the span of my system matrix, and this is just the energy, that's the maximum amount that I can decrease the objective by. So what we're able to say is that if we choose small enough regularization, because that biases your solve, so that's why it's kind of small here. If we choose a small enough regularization, and we sample enough columns, okay, And here, the number of columns we need to sample is some function of M, R, our regularization, the failure probability, and the precision that we want. If I sample enough columns, then I get a large fraction of the possible decrease with probability of at least 1 minus delta. Okay. So contrast this to if I just used the previous sketching results for just solving linear systems, would say that the error will increase by at most a small amount. What we're saying here is that the error will decrease by a large fraction of the best possible decrease. Okay? Now the question is, how many samples do I need? And by the way, I'm just doing column sampling here because that's like the simplest type of, these are uniform column samples. This is the simplest kind of sketching to talk about, but you can get, like the theory is all generalizable to different forms of sampling in the usual way. Okay. So what is this sample complexity? So intuitively, it just needs to be large enough to ensure that when I sample constraints, I don't change the geometry of the least squares problem. So what do I mean by the geometry of the least squares problem? Well, when I sample constraints, I'm changing the angle between my residual and my system matrix, essentially. Okay? So what I want is undersampling the angle between my residual and my system matrix, this thing here, should be approximately preserved. Okay? So this is the error in approximating that angle using sketching. So if I sketched like here, so I selected all of the, if I selected all of the columns, S transpose would be the identity, and this error would be 0. Okay. But in general, this thing is just close to the identity, and you want this to be some small fraction of the angle. Okay, does that make sense? So that's the intuition. And I also want the range space of M to be approximately preserved under sampling and regularization. Okay, so imagine if there was no regularization and no sketching, this would be exactly the projection onto the row span of the matrix M. It would be this thing. Right? This looks familiar. If S was the identity and lambda was 0, that would be this projection. So what I'm saying is that when I use regularization and sketching, I want this thing to be semi-definitely close to the projection matrix. Okay, and these gammas, is that gamma? Yeah, that's gamma. Yeah, I want those things to be close to 1. So that semi-definitely these operators look the same. All right, so now what we can show is for different forms of sketching, F scales like we want. Basically, we need to select R constraints. Remember, we have R unknowns in each row of A. So it turns out this is the number of constraints that we need to sample. Okay. And that will ensure that both of those conditions are satisfied. So here's just an outline, a very high-level outline of how we prove it. So what we do is consider delta here is going to be the difference in our factor matrix A after we solve for this update using the sketch linear system. This is just algebra. You can show us this right here. Okay, so it's the residual times our system matrix, but you see the effect of sketching here, and this is the usual. If we had solved the linear system exactly, well, this would be the identity, that would be 0. This is just the usual way of solving the linear system. Okay, so the decrease in the true objective function is a quadratic function. So its Taylor series expansion is going to be exact. So we're looking at this minus this is my decrease. So it's this minus the previous a plus my update. And I can get this expansion here. So I see it's a linear term in delta and a quadratic term in delta. Remember, this is the decrease. So I want this to be as large as possible. So I want this to be small, and I want this to be large. So you just do some careful estimates, and we're able to show that both of these things are proportional to our optimal decrease, but it's just the case that T1 is larger than T2, so we do see some decrease. All right, so that's the basic idea. And now let's talk about the intuition we can get from that theory. Okay. So the theory said we need to choose our sketching rate to preserve the angle between the residual at time t and our system matrix. And in order to do that, we can expect that that sketching rate needs to change over time. So at the start, we can imagine that our residual is going to be very close to our system matrix. Okay? So once we start our initial, the first few iterations, we can gain a lot by sketching very inaccurately. We can throw out a lot of the constraints because it's easy to preserve the geometry of the system because it's just, there's so much of the residual that's in my system space that I can sketch aggressively and still make progress. But when I'm near to optimal, the usual thing, then my residual is going to be nearly orthogonal to my system matrix. So to preserve this angle, right, because you can imagine if they were exactly orthogonal and I sketched even a little bit, they're no longer going to be orthogonal. Okay? So the closer they are to being orthogonal, the more I have to preserve the full constraint set. So near convergence, these have a large angle, so I'm going to have to do more expensive sketching. Okay? All right, so that's something to take away. Okay, so now we're going to talk about relating, we just guaranteed decrease in the objective, right? And I said that you can relate that to the size of the gradient of the objective. Okay, so let's look at the gradient of the objective. It's just this. Okay, you can compute that as the residual times the transpose of the system matrix. And I want to relate this to the amount of decrease that I get. So I can just inject this projection. It doesn't change anything, right? Okay, and now I'm able to take advantage of this injected projection to show that the gradient of this is going to be less than just the 2 norm of this times the Frobenius norm of this thing. Okay? And now remember M is B factorial product C. So I can upper bound the 2 norm of this by the 2 norm of B times the 2 norm of C times this is my I know that my decrease is some large fraction of this. Okay? So now I can plug in this, right? So I have a lower bound on this thing by bringing this over here. Okay? So this thing is greater than or equal to this inverse times the size of my gradient. So if the 2 norm of B and C don't get too large, then I see that this says that the decrease looks like the size of the gradient. And that's the key result that I need to just apply some standard results on optimization using proximal regularization. And this gives me my sublinear convergence for this algorithm. Okay, so I need to make some assumptions. And these are standard assumptions, okay? Standard, not necessarily reasonable, and this happens all the time, okay? So we assume that these gradients are block Lipschitz, okay? That's an unreasonable assumption, but it's standard. Okay, and we say that the constant is bounded by L along the solution path. We don't know this a priori, but we assume it. And then this is what we guaranteed. We said that sufficient decrease is achieved at every linear solve with this probability if we chose our sketching rate based on that angle. Okay, so we get these guarantees that at every step we're basically decreasing proportional to the size of the gradient. So we put all that together and we make some assumptions about how this decrease and the amount of regularization are related. And we conclude that after t iterations, we will have seen a sublinear approximate critical point. Okay? And our failure probability is going to look like that because there's a failure probability at each step. Okay, so again, suboptimal, but sketching is really this is sort of the best sort of guarantee you can get theoretically at every step for sketching. Okay, so what we guarantee is that at some point in those first t iterates, one of these points had a small gradient. Small meaning on the size of 1 over the square root of t. So that is the result. So sort of the standard result for optimizing a non-convex function using a first order algorithm. All right, so that's the theoretical result. We showed that in principle, if we were able to determine these sketching rates, so if we were able to somehow know ahead of time what these angles were going to be at every iteration, we could choose the sketching rates, and that would guarantee us convergence to a sublinear critical point, approximate critical point. But now let's talk about practicality, right? Okay, so to get a concrete algorithm, we have to assume that a good regularization rate is known, and then we can ask, how do we sketch? Okay, so this goes to your question, which is, how do we know a good regularization? We don't, but we just assume. And now we're going to focus on this question of how do we sketch. So like I said, Richard Peng's work and his collaborators said that you can use the leverage scores to figure out what are the important constraints, and then you fix a sketching rate. So you say, I'm going to choose 70% of those constraints. And then Tamara Kolda's work and her co-authors said we can randomly rotate these constraints so that all of the constraints are equally informative, and then we can just sample from those, again, with a fixed sketching rate, so say 70%. Okay? But, in practice, we don't know what those fixed sketching rates should be, and in fact, we can show empirically that fixing a sketching rate a priori turns out to not really converge better than ALS. So you can just go ahead and use ALS. It's kind of like using SGD without decreasing your step size. Okay? It's a bad idea. All right, so that's the question. The practical question we're going to focus on is how to choose our sketching rate. Okay, so the key observation is that this is an iterative process. Okay, so just like in SGD, the closer we are to convergence, we expect that we need to sample more constraints to ensure progress. Okay, and because it's an iterative process, we expect the performance of a given sketching rate historically is going to be predictive of its future performance. So this suggests that we can come up with some online approaches to learning the performance of the sketching rates. So there's this explore-exploit idea. Okay, so this is the problem we pose. So we let the user specify n sketching rates. Okay, so let's say 5 sketching rates, 500 sketching rates. And what we want to do is choose the best of these sketching rates at every iteration, where by best we mean the sketching rate that maximizes the reduction in the error while minimizing the runtime. Because what we really care about with sketching is we want to make as much progress in as little time as possible. Okay, so that's our goal. So what we do is we use a bandage approach. We use a label-efficient multiplicative weights update algorithm. So this is a very basic approach to bandits. Okay, so one way to do this, right? One way to do a bandits approach to choosing our sketching rate would be to, at every iteration, we evaluate all of our different sketching rates. So we do ALS with these different rates, and we measure this objective. So how much did our objective decrease using that sketching rate over how long it took to solve using that sketching rate, okay? And then we would assign weights to the arms based on these losses, okay? So what we want is that the losses with, where this is more negative, right, is we want this to be smaller than this. So when this is more negative, we want to increase the weight on that arm of our bandit, okay? So we want to increase the probability of selecting that arm. So this is what we do. We do an exponential update here. Okay? So if this is negative, eta here determines how aggressively we increase the weight on that arm. Okay? And then at each iteration, we select our sketching rate based on these probabilities. Okay? So we normalize these weights across the arm so they become a probability, and then we use it to select the arm. So that's going to tend to select the arm with better performance. But the issue is, if we actually had to evaluate these losses for every arm, so for every sketching rate at every iteration, that's going to be expensive. Okay? So that's why we're using this label-efficient version of multiplicative weights update. Okay? And the idea is, at every iteration, we flip a coin, and if that coin comes up heads, then we pay the price for updating the weights on all of the arms. If it comes up tails, we don't update the weights. Okay? So we're amortizing the cost across roughly, 1 over epsilon. 1 over epsilon draws. Okay? So that's why we call it label efficient. So we have two parameters we need to select here. Eta, which determines how aggressively we update when we update, and epsilon, which determines how often we update on average. Okay. Does that make sense? All right. So here's our recommendation. So basically, to amortize the cost, we take epsilon to be about 1 over n, so that if we have 500 arms, on average, we update the weights for those 500 arms once every 500 solves. So we're amortizing the cost. Okay? And we also recommend taking one arm to be solving the full system. So sketch the full system, because then that ensures that convergence is going to be possible, because you could, if you need to, always choose that arm. And then the usual arguments for multiplicative weights algorithms gives us a regret guarantee on this. That's pretty weak, so I'm going to skip that. Okay? You get some guarantee, but like I said, it's weak. So let's get to the numerical stuff. That's the interesting part, right? Okay, so like I said, the theory on that regret is kind of pessimistic. But in practice, importantly, we see that this multiplicative weights update algorithm has a better time accuracy trade-off than non-sketch CPD ALS. Okay? So here, paraslice is just parallelized CPD ALS, and these are also parallelized. This is all in Spark. Okay? And we're looking at using different numbers of sketching rates. So we chose our sketching rates between 10 to the minus 6 and 10 to the minus 4, I think, evenly. And like I said, we fixed our regularization parameter from the start to this 0.01, and we averaged these results across 30 runs. So we'll see results on standard deviations later. But here, we're plotting the time in getting these low rank approximations. So this is a 100 gigabyte synthetically created ill-conditioned tensor. We're getting a rank 50 approximation. We run for up to 5 minutes. Yeah, and here you can look at the progress with a different number of arms. So you can see if you use 1,000 arms, because you're on average only updating every 1,000 iterations, you can see you make some progress initially, And this is because there's a lot of progress to be made. And after that, you've already made that progress and you're not updating the weights on your arms, so it's not doing a very good job of continuing to select a good number of constraints to use. Right? So we can expect if we keep running this, eventually we'll see that it did update and it drops down. Just like you can see for 50 arms, this is what happens. You kind of see this saltation where it kind of levels out, and then, oh, I updated the arms here. Now it levels out again, and I updated the arms. Okay. So for, say, 5 arms, you can see that this works very well because you're sampling from the arms more often. Okay? And again, this is just ALS, so repeating ALS. Okay, and then, the sanity check, you could ask, what if I randomly chose the sketching rate? So here I'm doing random choice of sketching rates with the green. This is a random choice of sketching rates. And these are different types of sampling. And this is, again, standard ALS. Okay? So here, this is what we were using. So this says uniform row sampling. It's really uniform column sampling. So this is what we're doing here. Okay? And this is with, I forget, I think this is 10 arms. So we're using 10 sketching rates in the same interval, the same amount of regularization. And we can see that we're performing well here when we use a combination of the multiplicative weights updates and just column sampling. Okay? And again, that beats out parallel. And we can see this is if we just randomly selected the sketching rate at every iteration. Well, that performs really bad, so you do need to intelligently choose the sketching rate. Main takeaway from this. All right, so here are some pictures. So like I said, one of the uses for tensor decomposition is hyperspectral image processing. So here we just took some standard hyperspectral image data set, and then we reconstructed it using standard CPD ALS and our proposed algorithm, and the results are effectively identical. Right? So whatever it's worth, visually, they're identical. Okay? But this decomposition took about 1/3 the time of the ALS decomposition. Okay, so we get this nice trade-off between accuracy and speed. Okay, and again, here is another example. So here, this would be like from application to background subtraction. This is a pretty, again, this is like a standard data set. It's a video of a guy in a park sitting on a bench. So the background isn't changing very much, just the foreground. So anyhow, you can take your low rank decomposition using ALS or our algorithm. The difference is basically nil. And again, this took 30% less time than the standard ALS algorithm. Okay, and now to compare, we can compare to standard ALS. Okay, so this is standard ALS. This is standard ALS plus regularization. These are just parallelized. And this is our algorithm, which is also parallelized. So here we ran these. What is this? Okay. Forget exactly how we decided the stopping conditions, but we see that we get a lower error. Okay. The variance is higher because there's more randomness, right? Because we're choosing between different arms. And the time is also lower. There's higher variance in the time, but even accounting for that, the time is lower. Finally, so in conclusion, what we've shown is that this sketched regularized ALS has the sufficient decrease property. That's the important thing. And therefore it converges sublinearly. And then we introduced this multiplicative weights update algorithm for a practical way of selecting this sketching rate. So I think the takeaway from this is just regularization and the sketching rate adaptation are useful ideas for tensor low rank approximation. And indeed, you know, this idea of thinking of sketching as an iterative process is something that we see being worked on right now for even just standard matrix problems. So I think it's just a direction that is going to be fruitful and lead to more practical algorithms. So that's it. Do you have any questions?
So we're about 5 minutes over the official end of time, so if people need to go, we can. Otherwise, maybe we can take a quick question or two and then informally ask questions. I know Alex needs to go.
By the way, if you want, you can find this paper in Iceland.
So have you explored the lambda like going to 0?
Yeah, no, I don't have any, like the sort of straightforward way to do that would be to add the different values of lambda as new arms in your bandit. So then you have like this product space and it's going to be very expensive to consider multiple values of lambda. So I don't have any other thoughts on how to do that really.
I'm just thinking like take lambda, like have lambda t, like whatever you set it at, you have 0.001.
Yeah.
But then just at every step, you know, like it's just 1 over t, and just keep going down towards 0. I'm just curious how that might.
I mean,
but it's still not the same problem. Like your original problem is like you want to minimize it without this regularization. So in some sense, you know, you're getting closer to finding your solution, but you also want to get rid of this other term eventually. Kind of,
yeah. You know. So the issue is if you look back at the swapping plot. So what can happen is, as we're close to convergence on A and B, let's say, if they're ill-conditioned, they can really slow down the convergence on C. Because they're close to those two ill-conditioned factors, so then the update equation for C is going to be very ill-conditioned. So I think you don't want to necessarily let the regularization just go to 0 as T increases. But it's definitely an interesting question to consider. Even for regularized ALS, I don't recall seeing anything on theoretical guarantees if you change lambda, or how you should change lambda.
Have people looked at what happens to this whole leverage score and whatnot sampling when you start introducing error into your tensor? Or should I be thinking of this as you're like solving this least squares problem and you're trying to find the best like low rank thing to inherit already and I can just kind of apply it?
Yeah, that's a good question. So the error would be in X. And that would propagate to A, B, and C. Yeah, that's a good question. So I think Ilse Ipsen has some like perturbation results for leverage scores that maybe can answer some of that. But I don't know off the top of my head.
Yeah, I guess what I'm imagining is like if you have like some column that is really messed up, and it's going to seem really important, and you're going to start choosing it.
For sure.
Which seems like a worry.
Yeah, no, that's a great, I think it's a great question. I don't know the answer, it's a good question.
We are now 10 minutes over the official end time, so maybe we should thank Alex again, and we can